All right, so maybe just sort of a short short note on terminology. We're not going to prove anything in this video. So it's really just a definition. And if that's the following, if S is a discrete subset of an open U, and F has poles at points S, then we say that then F is meromorphic. Right? Now, what we can do for meromorphic functions is we can actually write F as a function into the Riemann sphere by just saying that Fp is infinity if p is in S. So F was not defined before at points of S. So you can just define it to be infinity as long as those are poles, right? Why does that make sense? I mean, we have those are poles, so we do have that the limit as d goes to p of f of z is infinity if p is in S, right? I mean, all those are poles, right? So it makes sense to just set the function to be infinite there, right? So we really have not a complex valued function, but a Riemann sphere valued function. Now, sometimes this is called a, we would say that this is a holomorphic function. It's a holomorphic function into the Riemann sphere, right? We'll just call them meromorphic functions. And I'll write this as a meromorphic, I'll say this is a meromorphic function, right? And it really means is this, right? It's holomorphic function except poles, right? I mean, you can, we've looked at this a couple of times, right? I mean, if I have, why does it make sense to call this a holomorphic function? Well, if I look at 1 over f of z near a pole, right, then it's just, this guy's just a 0, right? And so this guy actually has a removable singularity. It actually extends to a holomorphic function which has a 0 at that point. And actually, it's going to be a 0 over the k if the pole was over the k, right? So it makes sense. And so that's really the way that we mean that we have a function that's holomorphic as a C infinity value. Well, we really look at, well, what about those values at that are infinite? We just look at this thing, and is that a holomorphic function?